Why is the quantum mechanical model elegant for the periodic table? Imagine trying to organize a vast library where each book is an element, and the way they are arranged reveals their secrets. That's what scientists have done with the periodic table. But how do they explain why elements in the same column share similar traits? The answer lies in the quantum mechanical model of atoms. This model is elegant because it shows how electrons behave inside atoms, which determines an element's properties. Instead of fixed orbits, electrons are described as existing in regions called orbitals, which are like clouds of probability. These orbitals are defined by quantum numbers, which tell us where electrons are likely to be found and how they move. The principal quantum number indicates the energy level or shell, while other quantum numbers describe the shape and orientation of the orbitals. Electrons fill these orbitals starting from the lowest energy, following the Aufbau principle. Hund's rule states that electrons will occupy degenerate orbitals singly with parallel spins before pairing up. The Pauli exclusion principle makes sure no two electrons have the same set of quantum numbers. All these rules explain how electrons fill the atom in a specific order. The periodic table's structure matches the filling of these orbitals. The s block elements fill the s orbitals, the p block fills the p orbitals, and so on. This pattern makes it easy to see why elements in the same group have similar chemical properties. They share the same valences electron configuration, which is the outermost electrons involved in bonding. What makes this model so impressive is that it turns a simple classification into a detailed, predictive system. It explains why atomic size changes across periods, why ionization energy varies, and why electronegativity trends occur. It also shows how the structure of the atom influences the behavior of elements. Historically, this model marked a major step forward in understanding matter. It moved beyond classical ideas of fixed orbits to a probabilistic view, where electrons are described by wave functions. This shift was a key milestone in atomic theory and our understanding of energy at the atomic level. Practically, the quantum mechanical model helps scientists predict how elements will behave in different situations. It guides the design of new materials, helps explain chemical reactions, and underpins modern technologies like semiconductors and lasers. It even forms the foundation for emerging fields like quantum computing. In short, the quantum mechanical model is elegant because it provides a clear, consistent explanation for the organization of the periodic table. It links atomic structure directly to the properties of elements, making it a true milestone in the history of science and discovery.